All right, hello and welcome. Are you ready? Because it is time to learn about functions. We're going to learn how to make our own. It's going to be wonderful, okay? It's going to be great. And the idea is, I started drawing a little bit, you probably think by now that the main functions that you've been writing are probably huge. You've got a million lines of things, and then you have your return 0 at the very end of this, like, textbook size thing. Okay, we can solve that. We can make our own functions. We can split this all up so that instead of like one huge main function, it's just, okay, yeah, main. It does what it needs to do. It gets us started, but like it's going to call one function, f1, which maybe needs to call f2 and f3 to do some work, and maybe f3 is going to do some more work by calling f4. And it's just wonderful because we can split up our code into just a bunch of logical chunks of things, okay? So here is the skeleton of a function definition, and I'm going to use the one we already know and love, okay? So this is main. We already know how to do main. Let me show you why this is just a normal function definition. It works for any kind of function. It doesn't have to be called main. So there's always this thing called a return type. That's the return type right there. Maybe I should put like, I don't know, numbers. 1 is the return type. The function name, that's 2. That's main. And then you put some parentheses and your function parameters, if there are any. You're going to put them here. That's 3. And then you have the body of the function, just like your if statements, your loops and things. You put what happens when the function gets run inside of its body. That's 4. And then part of the body is called the return statement. That'll be 5. And you can have multiple of these, but this is what happens when you want to give something back. Okay, returning is the process of giving something back. Okay, we'll talk about this all in detail, but these are all the little pieces that make a function. Okay? And I'm using main as an example because you already know and love main. We can generalize this, okay? Let's write our first function that isn't main, and let's write it as a function that adds 2 integers, okay? So it's going to take, we're going to take 2 ints and give back their sum. Okay, are you ready? So it's going to look like this. It's going to be, well, what's it going to give back? It's going to give back an int. An int plus an int is still an int. And maybe we can call it, I don't know, add. And then it's going to take 2 parameters, 2 things that we're adding. Int x, int y. These can be any name, but I'm going to call them x and y. And then we're going to do our work. Okay? That is the idea. That is the hope. Are you ready? So I'm going to go to my code. So I'm going to actually, just for fun, use a different editor. Today we're going to use Vim, and we'll see if it's any more fun. It's going to be completely in the terminal, this lecture today. I'm going to say Vim, and then we'll say add.cpp. And this is going to pop me into my editor. It's very similar to the Emacs that I already showed you. And we're going to say int main, and instead of like saying, okay, yeah, let's get x and y, or let's call them a and b, we're going to get them from the user, enter 2 numbers. Instead of doing this, instead of saying the sum is, instead of doing this, x plus y, I'm going to make a function that does this. Oh, sorry, a plus b. I'm going to make a function that does this instead. So, no more this. Oops. No more that. But instead, we're going to say add a comma b. Okay? That's what we're going to do. And I guess I should add a space in all of these. And then I'm going to make my function called add, okay? So watch me now. It returns an int, it takes two things, x and y, and then what it's going to do is, well, it's going to give back the sum of x and y, okay? Return x plus y. See that? So this is how it works. This is how it's going to be. And let me show you. Let me show you it running. Okay. So, and then we'll talk about it some more. So no, I'm going to open a second terminal. I'm going to say, no, I guess I should actually call it something. Let's say add, enter two numbers, 2 and 3, and their sum is 5. So what's happening here is I'm saying in my code somewhere, add x, or add a and b, and that's going and running. That's essentially telling C++ to, hey, go run the add function with x set to a and y set to b. That's what it's doing. That's what it's telling C++ to go off and do. Okay? So x becomes, it gets the value, that was the first parameter, the first argument, a. Okay? X gets set to the a, that was the first thing, and then y gets set to this b, because that was the second thing that we passed along. So up here, in this function, at least the way that I'm using it, x is equal to a, and y is equal to b. Okay, that's what they're set to. And now I can use x and y instead here and give back the answer, give back their sum. Okay? So it's very simple, I know, but it's working. It's adding the 2 and the 3 and making 5. Okay? So that's our first function. Aren't you excited? You can also overload functions, we say. So you can have multiple functions with the same name. And that's called overloading a function. Okay, so we can make our add function for doubles and strings, for example. Watch me. I can just change the types around. Whee! So instead of ints, let's make it doubles. Yeah? Instead of doubles, let's include the string library and make it strings. Yeah? Bam. They all have pluses. All we have to do is give back the sum. These comments no longer make sense, of course. But here's what's going on. I can say cout add, and then 3.14, 5.67. And this is going to call the doubles add function. Oops. Okay, the one that takes doubles and returns doubles. Maybe I should say that. Yeah, so that is that. And let me show you this running. Oh no, because of that comment, it formats it weird. Let's move it up here then. Much better. Okay. Enter two numbers. Okay, 2 and 3, fine. But it's going to output 8.81 here. It's going to add these ones, and that's obviously not calling this function, because otherwise it wouldn't have decimal places. This one is being called instead. Okay? So that is add on doubles. Let's do add on strings. We can say cout add, I don't know, hi, space, and then mom. How about that? Bam. Hi space mom. All together. So it took x, in this case, as hi, and it took y, in this case, as mom, and it added them together and gave back the string that was their result. Okay? I hope you see how this is going to be very, very useful for us for the rest of the time, and that is our first function. Aren't you excited? So now I want to talk about another kind of function, one that just does something. Okay? Let's write a function to print hello. So So this function doesn't give back anything. Let me show you that. It's like, okay, I'm going to make a new file called hello.cpp. And again, I'm going to have a main function, and I'm just going to write a function call here with no parameters or no arguments. Let's make it be called hello, and the hope is, let's make this function, call it hello, that prints out hello. Yeah? That's all we want. I guess I wanted it to be lowercase. Why not? And so the idea is, it's not going to give back a value, it just does something for us, okay? So, it shouldn't need to return an int, right? There's no need for it to return an int, a string, a double, or anything like that. There's no point, because it's not going and returning something. So we'll come back to this, but we can do the rest of this. It's like hello, takes no parameters, its body is cout hello, maybe a new line. Oops. But what should the type of this be? It shouldn't be int, because we're not returning anything. Like that's wrong. The answer is, when you have a function that just does something, that doesn't need to return anything back, its return type is called void. Okay, void means it returns nothing at all. They're very useful. If you're not going to return something, you say that your return type is void in that case. Okay, so the function without the body looks like void hello. Okay, bracket bracket. That is the idea. Void is for when you don't want to return anything. Okay, so that is a G. Now, let me show you this running. Let me show you it making sense. /hello. And what it's doing, again, is the second we make this call, the program jumps up to here. It's like, okay, I'm going to run the body of this code, and, oh, it says to cout hello, so I better go do that. And then it's like, okay, I am done now. Back to main. Okay, and then it returns 0, because that's the last thing to do. I can call this function twice. There's no reason I can't. Okay? Hey, hello, hello. So there's no reason to not call a function multiple times. We can call our functions as much as we want, which is really, really nice. We don't have to copy any code like that or anything. It's wonderful. So that is two kinds of functions. One that gives something back, one that does not. And so let's talk about function calls in general now that we have the idea of how to actually define functions under our belt. So here's how you call a function. I know I've showed you this before. Let's just revisit the topic. You always have your function name. Okay? That's always there. You want to call this function. Let's do that. And then we want to call the function with the first argument being a and the second argument being b. Okay? So maybe if this is defined as int plus int x int y, for example, it's going to go and set a to be x and b to be y. That's how that's going to work. This is, oops. I said one thing and wrote another. My fault. That should be the 1, of course, and this can be the 2. Those are the arguments. And then you can optionally get back the return value. You don't have to get it back. You don't have to use it, but usually you're going to want to. Like if you want to immediately go and print this out, you can take it. You can get it back, and that is this whole process here. 3, I'm making a variable that gets back the result of a plus b. Yeah? And then the key idea I've been trying to hint at is the parameters in the definition of the function receive the arguments in the call. So that's this process right here. That's our for. Okay? when we run this function call, it's going to jump up here and set plus is x to be a. It's going to set plus is y to be b, if that was how we define the function. Of course, maybe we could call this z or something, and then it would all still be the same, but with z instead of x. I hope you see how this is working. So that is the idea. We have a in the call and x in the definition. Okay? So that is function calls. And now I want to talk about something that's quite confusing. Okay, there's a very subtle difference between returning something and printing out something. Okay? So let's step back and think about how we can use these two functions. Let's say I've defined them both, add and print hello. How can we use those in main? Okay? And the key is to assume that each call gets replaced with its return value, if there is one. Okay? So if I'm here in main, like this is my main right here, I can say cout, add 2, 3. If I wanted to, I can say int s for sum maybe equals add 2, 3. I can use this function because it's going to give me back an integer. I cannot use this function the same way. I can't be like int c equals print hello, because print hello doesn't actually give back anything. It's a void function. So this makes no sense at all. Okay, I hope you see that. Can't do this. You just have to call it by itself. You have to say print hello. And it's going to do that one thing that it's supposed to do. That's what void functions do. They just do a thing for you. And you have to call it alone by itself. Not inside of cout, not inside of an assignment statement, because when you do it that way, you're assuming that this is going to be replaced with whatever is given back to you. Okay? This function gives back nothing. Okay? That's the key difference. So it's incorrect to do this. Okay? This is, again, a huge problem. Like if I were to replace this with cout instead, I hope you see the subtle difference that this implies here. I cannot use the result anymore if I just see it out. Okay? That is the idea. So we're going to come back to this plenty of times, but I wanted to just throw it at you to begin with. Okay? So that is returning versus printing. This gives something back. And whenever you call it, it gets replaced with whatever it gave back, that thing that it's returning. Whereas this one does not. It doesn't get replaced with anything at all because it doesn't give back anything at all. And so you have to call it alone. It must be called alone. This entire function. Okay? And you can also do fancy things like add 2, 3, like plus 5. That's totally fine. In fact, let's go to that before I forget. You can say something like cout add 3, 4, and then times by 2. Because it gives something back, you're allowed to do that. See? So you can take the 7, multiply it by 2 to get 14. It's going to get replaced with whatever is given back. Okay, that's enough rambling now. Let's talk about going and breaking down problems in general. So we have something that we want to do, like make cornbread, and we need to come up with a bunch of little lists of things, like sequential things to do that get us our end goal, which is apparently cornbread. Okay, so let's talk about some ways to do that, because I know we've learned a few things. We have some tricks under our belt, and there are more, though. So I want you to think about this problem. How can I sum the squares of numbers? Okay, from 1 to 2 all the way to n. Okay, so for example, the sum of squares where if n was 3, we wanted to give back 1 squared plus 2 squared plus 3 squared, okay, all the way to 3, which is apparently 9, 10, 11, 12, 13, 14, I hope. That's our problem, and n could be anything, okay? So I want you to think about that. Take a second maybe, pause the video. How would you go about coding this up? And your idea might be like, yeah, I'm just going to write an algorithm. I'm going to write my little recipe, and it's going to work. But how do you do that? Like, where do you start when you're writing your algorithm? How do you think about this in a logical way? And the answer is, we have to go back to the definition. An algorithm, it's just a sequence of steps to go and solve any problem. And I guess I'm starting to teach you what is the goal of this class. So functions really help you get towards this goal. It's how to break down these big problems that I'm giving to you down into small bite-sized pieces so that you can then go and solve those individual ones, making a bunch of little tiny algorithms and bring them all together to solve the final problem, okay? So you just keep going until those little pieces that you broke your problem down into, like if this was the big problem, we can break that down into a bunch of little interconnected problems, okay? Things like that. And then, yeah, we keep going until we have something small and manageable, and we can write little functions for everything if we wanted to, and it all makes sense, okay? So I want you to be able to come up with these kinds of things, these kinds of algorithms, these steps yourself, okay? So I'm going to try and wean you off of like taking step-by-step instructions that I give you and implementing those. I want you to come up with the algorithm yourself. That is what's going to keep you moving forward in your programming career, okay? So I guess the idea, what I'm getting at here, is the programming process, the one that you're doing now, it can be formalized. And here are some good steps. Here's a good strategy to follow when you're trying to solve a problem, okay? First, you have to read the problem and understand it, of course. That's the idea. Then you have to get input, okay? Read the problem, read its input, and implement it, okay? So every single thing that you're trying to solve, usually it does different things depending on input, so you have to know how to get the input, and then you have to figure out how to implement it. And that's just the first step, okay? That's only the first step. There are more steps. And a big, big step is testing, okay? I'm going to talk about testing, if not in this lecture, maybe the next one. And the idea is we don't trust ourselves. We have to test our code to make sure that it's going to work properly every time we call it, or at least to gain some confidence in the fact that it is hopefully slightly correct at least. So that's what testing is for. And when we have giant programs like you're going to eventually have, there is no choice other than to test it. Otherwise you have no clue if it's ever going to work. Okay, so that is kind of the steps that I want you to follow when you're writing a program. And you should always like debug, always print some things for yourself to see if what you think in your head that's going on in the program is actually going on. Okay, so yeah, I guess that is my spiel, and I am going to give you a ton of practice as I do. So let's break down this problem into little tiny pieces, tracking how data moves around. That's very, very important. And then also for sequentiality purposes, that's a long word, you have to figure out what needs to be done before what. Okay, so let me break down this problem for you so that we can talk about how it's working. Okay, so the idea is, okay, we need to sum the squares. Summing needs to happen, okay? We need to somehow generate squares of things, and we need to somehow enumerate the numbers 1 through n, okay? Those are the 3 key things that I see going on here, okay? Do you see that? And the idea is, what's the order of these things? We need this first, right? We need to get 1 through n first so that we can then go and square them, right? And then, after we have the squares of all these numbers, 1 squared and 2 squared and 3 squared all the way to n squared, then we need to sum them together. Do you see that? That's the order of things. That's what needs to be done before what. That's the way that data is flowing, okay? We take these numbers, send them to the squaring function maybe, and then send those to the summing function, yeah? That's the hope. So that's the pieces of this puzzle, okay? That is how I want you to think about this. All right? So this is our steps. This is what we want to do. And then the next step, that is a very good one to do, is to write what are called a bunch of stubs. And let me, just check myself. We're going to write a bunch of stubs before actually writing the real code. So a stub, in case you were wondering, a stub is a piece of code that gives back the right answer. It's usually a function. A stub is a function that gives back the right kind of answer, but it's like a dummy answer. It just checks that the types are all correct and they all line up. Doesn't actually solve the real problem yet, okay? It's a nice starting point for the final problem, okay? So it gives back some element of the proper type. Just to test that everything's going to work well together. Okay, so let's write a bunch of stubs before we actually write the real code, and this is our problem again. Okay, so are you ready? Make a new file called, I don't know, sumsquares.cpp. And the idea is we're going to need to do a few things, okay? We're going to need to, well, eventually call this function, make a big function that does the whole darn thing. So sum squares from 1 to, and then give a number like 5 or something. That's the first step. Oops. That's what we want. That's our end goal. But how do we get there is the real question. So what does this need? What does this function need in order to run? That is our job as a programmer, to figure that out. So it's going to take an n. Like, we're going to sum the squares from 1 to some variable number n and give back that sum as an integer, okay? So we need to figure that out. And then, inside of that, well, we're probably going to need to know how to square things, right? That would make the most sense. So I'm going to maybe need a square function. Take an integer x and give back the squared version of it, right? Return x squared. How are we going to do that? Well, that's part of what we need for this one. Eventually, somewhere in here, we're probably going to call square. Okay, this is how you break down your problem. Like, this is what I need to do, and it needs this smaller piece. That's the point. That's the hope. Okay? And then we're going to eventually sum these all together. So just for fun, let's write a sum function, because why not? Or let's just steal the one that we already made. We'll take add. Okay, so we're going to sum using add. Maybe let's just call it sum. Why not? We're going to sum a bunch of squares. Okay, that's the idea. That is our end goal. And okay, so those are a bunch of things. And let's write stubs first. Like, let's pretend that this didn't actually exist. I don't know how to implement this yet, but I know that it's going to eventually give back an int. So let's say the answer is always 42 when it's an int. Okay, return 42. I don't know what I'm doing, but I want to just test that everything's going to work properly. Test that it's going to compile properly. Okay, so these are stubs right now. They're just returning back a weird dummy answer, but they're the proper type. Okay, that's very useful. Whee. So some squares. And hey, it runs, it compiles, and it always gives back 42 no matter what you give it. Okay, so that is a great starting point. And now, because we have stubs, we know what needs to be done, and we can write the proper implementation for sum of squares. Are you ready? Okay. Dun. And yes, I guess I called it something different, so let's call it sum of squares from 1 to in our write-up. Okay, let's do this. So the idea is, first, we need to enumerate 1 to n. That's probably going to scream loop, right? Needs a loop. Needs a loop. And then we're going to need to take those numbers and square them. And then sum them all together. Okay, that is the hope. So let's get started. So we're going to need to first enumerate from 1 to n, create all those numbers. A for loop seems like the best way. Int I equals 1, I is less than or equal to n, I plus plus. So now I have all the numbers from 1 to n. And now I need to square them, square I, and add it to my sum. Okay? So I'm going to make a variable that is called sum, and that is going to ruin everything, I think, because I have a function with the same name, but we'll deal with that in a second. How about this is capital sum? Would that work for you? Okay. So the idea is we need to first square I, int I squared equals square I, and then we're going to go and see if we can then add that number into sum. Okay? That's what we need to do now. Sum equals sum plus I squared. And then at the end of this loop, sum should hold the final answer. Return it back to whoever wanted it. So we can say return sum. Okay? That gives back the final answer. That was our integer. That was the sum of all the squares from 1 to n, assuming all of this worked properly. Okay? And so it's not yet correct because it's going to always return 42 whenever we try to square something. And actually, we should probably use sum as well instead of the plus. Let's say sum, comma, I squared. How about that? And so now it's going to get really weird as well. It's always 42 is the final answer. So that's no fun. So let's now go and implement all these stubs. Okay, so what's something squared? What's x squared? Well, it's x times x. What's the sum of x and y? Well, it's x plus y. And that was a quick solution. And it seems to be 55 is the final answer, and we can quickly confirm that using Python. 2 squared plus 3 squared plus 4 squared plus 5 squared. Hey, that is the answer. Cool. So I have confidence in this now. So we just made a function that sums all the squares from 1 to n. The sum of all the squares of 1 to all the way to n. Okay? Hopefully that process of breaking things down and making little stubs was helpful. It's going to be very useful when our functions get very, very large and numerous, but that is the idea. And so that is some squares from 1 to. Let's now talk about how to do something cool. Okay? So in general, it's bad style to have your main function int main way down here with a bunch of function declarations and definitions up here. Like this is super long, then you have another function that's super long. The solution is to move all these down below main. Okay? And that's not going to work originally. Okay, we need to do some more things after this, but that's a start. This is a lot cleaner because you know immediately now, oh, this is what my program's going to do. It's going to call this function. But the issue now is C++ has no clue what these functions are. It's like, you're trying to use this function, but I don't know what it is, dude. And so the problem is because it comes after, it hasn't seen it yet. So when it's here, it's like, I have no clue what's going on. So the solution is, well, to declare that the function exists up here with a semicolon, like a variable. This declares that this function exists. It will be defined later. It's a promise that it will be defined later. Okay, and I can do that for all these functions. I can say sum, boop. I can say square, boop. And then we can declare them, declare the fact that they exist. And it's a promise that they're going to be defined later somewhere. And so this is the general idea. So declare all your functions up here, and then define them below main. That is pretty, I hope you see. And so this will compile, and we'll run. 55, cool. And yeah, that's the main idea. So this is what you should do. It's much cleaner this way. All right? And because I say this is a promise, you have to keep that promise, because if you don't define the function and say how it works, then C++ has no clue how to use the thing. It's like, you're telling me something, I can't generate this function out of thin air, dude. And so it's going to show you what's called a linker error. It's like, I could compile the program, yeah, I understand what you want from me, but you need to show me the code for the sum function, dude. I need that. And so this is called a linker error. The L means linker. Okay, so just make sure that you give it the real stuff, the full file, and then it will correctly work. Okay, so that is breaking down functions. Hopefully this example was kind of cool. We are summing a bunch of things, summing a bunch of squares of numbers from 1 to n, and I showed you how to break this up into pieces, and then how the data needs to flow on down the line. Okay, so that is breaking down problems. And now, for the last little subsection for today, I want to talk about testing. Okay? Testing is how to make sure that things are correct. Okay? How in the world do we know when our function that we write does the right thing, actually? We have no clue. We think that we did it right, but we are usually wrong about that. Trust me, I know from experience that I am usually wrong when I write something. Okay, so it would sure be nice to know if our function always works, no matter what input we give to it. And maybe our function takes a number, it takes an integer, and we know that integers are 32 bits long. Well, there's only about 4 billion of those. Hey, we can try them all and make sure that they do the right thing for each of them, right? That would only take like a few decades to go and check by hand. But obviously, this is not feasible for every possible function. As I'm sure you can imagine, the second you start taking 2 ints instead, now you have 4 billion times 4 billion combinations. You see that? That's no fun. So it is possible, and you might learn about this if you continue in your computer science career. It's possible to prove that functions are correct without having to try all 4 billion things, and to know that your function is going to work perfectly every single time. But what I'd like to tell you now is is an easier thing to do. That is very, very common. It's much more common than trying to prove functions correct in industry anyway. We're going to do what's called unit testing. We're going to write a bunch of unit tests. Okay? So that is the idea. What is a unit test, you might ask? Well, it's when you take a very small chunk of your program, and that's usually a function, so for our intents and purposes, it will be a function, and we write several test cases for that one chunk to make sure that it's doing the right thing and we are happy about it. Okay, so that is unit testing. And so let's make something and test it. Okay, let's write a factorial function. Let's think about things. So factorial, it's going to, we want to calculate 5 factorial or something, and it needs to give back the result, which is, I don't know, whatever this is. Okay, so what is the return type of factorial? Maybe we'll call it factorial. We want to call it like this, factorial of 5. What does it give back? Well, it's a number. It's going to be an integer. Well, are there any parameters? I kind of just gave that away. There's just one. It's the thing that you want the factorial of, right? There's 1, and it's an int. Okay? What should the name be? I think we've decided on factorial. I'm happy with that. At least I said it here. So maybe we should call it factorial. We could also call it fact if we wanted to. We can call it whatever we like. We can call it factorial. And now we want to go and write the stub. Okay? So, bam. This is how we do it. So I'm going to make a factorial.cpp file. And, I don't know, we'll say cout factorial of 5. And now int factorial takes some number n, and then it's going to be a stub right now. So let's say it returns 42. That's the final answer. Okay, so this is going to not work, and that's the point. So factorial so it gives back 42 for the answer of factorial of 5, which I'm pretty sure is wrong. Okay, so let's fix this. Let's slowly but surely make sure that the factorial function is right. Let's write enough test cases to make sure that we are confident that our function is correct. Okay, so the idea is a test case is called this when it's a Boolean expression. So it's just something that you're comparing. Okay, you're comparing what you expect the function to do and to give back with what you got. So for example, factorial of, I don't know, 4, we need to make sure that that is equal to whatever 4 times 3 times 2 times 1, which is 4 factorial, really is, which is 24, right? We need to make sure of that. That's one test case. Okay, that's one test case. Another one is like factorial of 3. That should be equal to 6, right? And then factorial of, I don't know, 1. That should be equal to just 1. Do you see that? These are test cases. If we check all these things, we can be pretty darn confident that our factorial function is doing the right thing. Okay? So, let's do this. Are you ready? Let's figure this out. Actually, let's just make sure. Yes. Okay. Let's implement this function as best as we can and make sure that it's correct. So, actually, let's write the tests first. Let's make sure, like, if factorial of 4 is not equal to, if it wasn't what we wanted, if it's not equal to 24, then we have a problem. Okay? Test failed. Then we can say cout failed factorial of 4. New line. And then we'll do the same for factorial of 3 and factorial of 1. Okay? So 3 needs to be just 6, right? And then 1 just needs to be 1. And this is now factorial of 3 and factorial of 1. And so notice that we have failed all of our tests. Watch me do something silly. Change 42 to 24. So now it's correct sometimes. And this is the key. Oh, we didn't pass, or we passed the 4 test. We failed the other 2 though. And this is key, because we want to make sure that we're thorough. Okay? We want to make sure that we cover all of the code that's running. Okay, and I'm going to show you what that means after I write the real answer. But notice that just writing one test is not good enough because I can just return that one answer. You see that? That's no fun. So that's why I have to give you multiple tests on your labs. So let's write the real answer now. So the factorial is a product of a bunch of things. So I'm going to start the product at 1, and then I'm going to iterate from I starting at 1, I all the way to n, or we can start at n and go downwards just like we normally do. And I is greater than or equal to 1, I minus minus. Then we can say product equals product times I. So initially I is going to be n, so product is going to start at 1, then it's going to be times n minus 1, times n minus 2, times all the way down to just 1. That's the way this function is going to work. That's the way this loop is going to go. Okay? And then we can return that product. And also remember semicolon, of course. So that should work. And notice we passed all our tests. We got absolutely no output, and that is the key. Okay? So we were thorough on our tests, and our tests cover this code. And the reason we say cover is if there was like an if statement, if there were some weird corner cases, if-else statement bodies, you want to cover both of them. You want to cover everything. You want to make sure that all of this code gets run, and we want to make sure that we are thorough enough. We're actually not thorough enough at the moment because we can give negative numbers still. We can give 0, and it will give back 1 as the answer. And I guess it's your job to figure out, is that okay? Is that good enough for our purposes? So we could even go further if we would like. So that is test cases. Let us continue, and I have some problems for you now, okay? So I would like you to tell me, what is wrong with this function, okay? So take a second. Hopefully you can understand it a little bit. So it's trying to square something. It's supposed to give back x squared or something. This x, it should give back. Square of 2 should give back 4, for example. But is it doing that? Let's try it. Let's try it right now. Square. If I call square of 1, then, oh yeah, the x is going to be 1, and we're going to give back x. Oh yeah, 1 squared is 1. That checks out. It's correct, isn't it? No, it's not. Because I think you can write a different test case that shows that it's wrong. Okay? We can test, hey, is square of x square of 2 not equal to 4? And this will be true because it fails. Okay? This will not work because square of 2 gives back just x. It doesn't use this variable at all. Bam. We just get 2 back. That's not 4. We failed the test. Okay, so hopefully you understand how you can write a test and exhibit a problem. That's going to be very useful to know how to do. Okay, what about this one? Is there something wrong with this? Can you write a test to tell me what's wrong? Okay, so take a second to look at this. This one's a bit more thorough, or not thorough. It's a bit more subtle. And so I'm going to go to tests.cbp, because why not? I'm going to copy this, I guess. There it is. Return the squared number. And why is this all weird looking? There we go. And let's say cout square of 2. Oops, sorry. This one actually works. So square of 2 is not the problem. Do you see that this is wrong? This is an incorrect function. Do you see it though? Oops. And then otherwise we can say like passed. It passes our test. It's going to work. Square of 2 passes. What in the world? Well, we can do more. We can do better. This is not the problem. Square of 2, yes, it is 4. But the issue here is this int. Do you see that? Because of that, this test right here will not pass. Square of 2.5. Or, yeah, I'm not really sure what this answer should be, so let me go and test it. That should be 6.25 apparently. But it's not going to give us that, because it's going to take this, it's going to square it to 6.25, and it's going to give back just 6, because this has to be an int. It'll give back 6 as the final answer. Oh man. Oh man, oh man. And also I shouldn't be comparing doubles like this, but you understand what I'm trying to do. We passed one, but we failed the other. Okay, that is the problem. And we can fix this, of course. I think you know how. You can just make this a double. But that just goes to show you that getting the right tests to cover the code, to make sure that everything is correct and thorough, it's not the easiest thing in the world, okay? Because square of 2, that is correctly 4, but square of 2.5 is not what it should be, okay? It's not 6.25, unfortunately. How dare it? So that is where I want to leave us, okay? So we've come very far this function, or this lecture. We've learned about functions. We've learned how to make our own that break down little problems into smaller bite-sized pieces. We've learned how to systematically figure out the way that code should be working, the way that data should be flowing in between multiple functions. And we've learned how to test our functions to make sure that they're doing the right thing. Unit testing is very, very important. It's going to make sure that we're not doing silly things like accidentally using ints instead of doubles. Okay? With enough tests, we can be pretty darn confident that our code is correct. And that is a very important thing to want. Okay? So that's where I want to leave you. We'll come back and talk about the stack in the next lecture. So I'll see you then.